Okay, people, let's get started. So please turn on your video if you're comfortable with this. Otherwise, get ready with the icons. So the plan for today is to keep working through the sections somewhat quickly, doing one example, perhaps from each section, covering the main concepts. I'm also open to doing anything that you want me to do. So if you have any particular topic or any particular exercise you want me to do, just tell me, I'll put it in the chat, and I will do that. I also have office hour after this class, so keep that in mind with any other questions you might have. All right, so where were we? We were talking about the integral test, and we stated it, and that is section 11.3. So we stated the integral test. And one of the most useful things about integral test is that we can actually find the difference between the sum and the partial sum using it. So let me write down what we need. Suppose an are greater than or equal to 0, and there exists f, which is obviously it has to be positive, continuous decreasing. And f of n equals an. Let's draw the picture to represent this information. So we have these positive terms, so drawing them as blocks like this. There's 1, 2, 3, 4, and so on. And if we have fn equals an, then that function exactly looks like this, right? Because right here we have f1, which is right here. This is f2, which is a2, which is right here. So this function exactly lives on top of our blocks, right? And we know, as the statement of the integral test tells us, and I explained a bit why, that the series converges if and only if the improper integral, so I'll just write it down, if the improper integral from any number a to infinity f of x dx converges, this is equivalent to the series converging. Again, we can start from any number because convergence depends on what happens to go to infinity, so the first, whatever, any number of terms are not important. Okay, that's the integral test, but the cool thing about it is that we have actually a way to approximate how close this series is to its partial sum using this stuff. So this, let's sort of expand this picture to the right. So imagine I'm looking at this picture to the right and I have these blocks. So I'm blowing them up a little bit like this. And suppose this here is n minus 2. Right here, this is n minus 1. This here is n. And then this is n plus 1, and so on, like this. So we know our function goes through the top right-hand corner, like this. And recall we defined n to be the remainder, which is what happens when we take the actual sum from 1 to infinity minus the nth partial sum. So it's like summing from k equals n plus 1 to infinity ak, right? So if we let s be this thing, we have that Rn, the remainder, is the actual sum minus the nth partial sum. Yeah? So let's see what it looks like on our picture. So the nth partial sum is like the first term, the second term, the third term, and so on. This guy, this is the nth minus 1, sorry, nth minus 2, this is the nth minus 1, this is the nth. Yeah? So all of these guys are summed in the Sn partial sum. And what's left are these guys here. Yeah? But we see that all of these guys are underneath the graph of the function from n to infinity. Yeah? So from the picture, nothing complicated, nothing difficult, nothing hard to believe. This integral is bounding above the Rn, the remainder. Yeah? And that allows us to estimate how close our partial sum is to our actual sum just by calculating this integral. Key point, we don't know what S actually is. We are not able to calculate it. Yeah? But we can calculate how close the partial sum is to this thing, which is just as good, for any purpose at all. So let's do an example. There are a couple of tests that allow us to estimate how good the partial sum is to the actual sum. This is one of them. The other one is the old series approximation test. Let's do an example for this guy. So, example, find how many terms needed to approx the sum from k equals 1 to infinity, 1 over n to, oops, let's call it n, 1 over n to the 3 to within 0.0005. Okay. Solution. All right, just to underline it, we don't know what this is. We don't know what this is. This is something we do not have the ability to calculate, at least with respect to this course, right? But we're still going to be able to approximate it with arbitrary accuracy using this idea, using this simple estimate. No? Cool. So what do? We simply create a function that's going to recreate these blocks, right? And it's easy to see it's going to be, since it has to be something like this, then this is the function that's going to do it. Yeah, this is a continuous function. It is decreasing. We are all good. We also know that this thing has improper integral, which is convergent, right? Because this 3 is bigger than 1, and we know that the integral of a to infinity 1 over x to the p dx is convergent if p is bigger than 1, right? We discussed this guy. So this thing is definitely converging, right? So this S, so S, which is the thing we're trying to approximate, this thing is some number. It is some quantity, right? Now we're gonna approximate it by this inequality, by this simple method, right? So we know that Rn, the remainder, is less than the integral from n to infinity of this function. And that is something we can just calculate, right? So that is the limit as r goes to infinity, right? And that's the limit as r tends to infinity. What's the antiderivative to get this? Let's do x to the minus 2. And if we do that, we have this extra minus 2 that we don't want. So let's divide that by 2. Right? And then the derivative of this thing will give us this thing, which is exactly what we want. And then we're going to take this limit as r tends to infinity. Let's pull out this minus a half. And then we just stick in r to the minus 2. Badly written. R to the minus 2 minus n to the minus 2. Yeah. Now as r goes to infinity, r to this minus 2 goes down to 0. Right. So all this is going to be is therefore just minus n to the minus 2. Right. So it's going to be 1 over 2 n squared. Oops. Is this correct? Yes, this is correct. Everybody happy? No? Thumbs up if you're with me. Thumbs down if anything's unclear. Okay, cool. All right, so we have explicitly this estimate, right? And what do we want? We want to have this within 0.005. So let's put this in fraction form. So 0.5 is 1 over 2. 0.05, therefore, is 1 over 20. 0.005 is 1 over 200, and 0.0005 is 1 over 2000. Yeah. So we want this thing to be less than 0.0005. So it's the same as requiring that Rn is less than 1 over 2000, like this. Let's double check. There's this. Yes, looks good. So that is implied by having that this thing is less than that amount. So if 1 over 2 n squared is less than 1 over 2000. If this was true, it would imply this, because we have this estimate that Rn is less than 1 over 2 n squared. Yeah? Yeah? So to get the logic right, so you don't confuse yourself, write down what you're trying to do. And what you're trying to do is ensure that you're within 1 over 2000. Yeah? So this is what you want. Yeah? And since you know that Rn is controlled by 1 over 2 to the n squared, yeah? Therefore, what you want is given by this estimate. So if you have this estimate, you have what you want. Yeah? Cool. So this is some completely concrete thing. You can just see what n will be required, right? So you do some algebra. Let's multiply both sides by 2, and what we actually have is 1000 is less than n squared, and that means that what we need is an n bigger than the square root of 1000. And the first integer n which we get, which is bigger than square root of 1000, will do the job for us. And square root of 1000 is like approximately 31.6. So running out of space. Let's put this 1 over 2n squared here. Is this. So need n such that n is bigger than 31.6. In other words, n is 32. Yeah? So we can get to within this incredibly small error by simply taking n to be 32. So if we sum this partial sum from k equals 1 to 32, that's going to give us the answer to within that level, right? Yeah? Cool. And that is power. That is power. This is considered one of the more difficult type questions on series, but I claim it's not difficult. It is not difficult. Because the actual estimate is not difficult, it is simply this picture. It's simply this picture. Yeah? Not difficult to understand, not difficult to remember, not difficult to believe. Yeah? And applying it isn't difficult either. Yeah? Because we have explicitly what the Rn is, we just do the calculation, get it in terms of n. Yeah? And then we write down what we want the remainder to be less than this error. Now we can write it down in terms of n, and then we just solve to see what n we require. Yeah? And obviously, the answer that we're looking for is the smallest possible n. Yeah? So it's also true if you take n bigger than 400, it's going to give you that estimate, but that's no good. We want the smallest possible n, and we can find it. We can find it with this tool. So. Okay, the simplest. Okay, first let's say what it's about. So, given an and bn positive, so everything we've talked about so far is for a series made up of positive terms. If we have the following relationship between an and bn, which is that an is less than or equal to bn for all n, right? Then we have some easy implications. We have that if the sum n equals 1 to infinity an diverges, this implies the sum n equals 1 to infinity bn diverges. And if the sum n equals 1 to infinity bn converges, this implies the sum n equals 1 to infinity an converges. And this is completely natural, right? We draw the picture. We have that the bn are bigger than the an, every single n, or bigger than or equal to. So these blocks I'm drawing will be the bn. Okay. And the AN are less. So this can be the AN. Right? This guy will be the AN. And we can just see that this is true, right? So if the AN diverges, the area underneath all of these red blocks is infinite. Therefore, the area underneath the BN blocks has to be infinite because they are bigger. Huh? Just immediately true from these pictures, right? And conversely, if the area underneath all the BN blocks is finite, it converges, that means the area underneath all the AN blocks is finite because they're all underneath. They're all a subset of the BN blocks. Yeah? So these are immediately geometrically obviously true things. Yeah? So this is useful in many cases where we want to understand some series which looks kind of ugly, but we can bound it above by a guy that is simple and that we know converges. Or conversely, we have an ugly series, we can bound it below by something which was simple and we know diverges. Yeah? So this is a useful, very simple test. However, it's not some kind of every situation applicable tool, because we can have examples like this. Suppose we have AN is 1 over 2 to the n minus 1, right? So we look at this and we go, okay, this thing looks like it's going down to 0 really, really fast, right? So we'd expect it to converge. So we might say, okay, well, we might want to bound it above by the thing that it's most like, which is 1 over 2 to the n. But this isn't true. This thing is not less than 1 over 2 to the n, it's actually bigger than 1 over 2 to the n. Yeah? Because on the denominator we take away 1, so we make the denominator smaller, therefore this number here is bigger than this number. Yeah? So we cannot simply bound this guy by a guy that converges, that looks like it, because the guy that looks like it doesn't bound it from above. Yeah? So we can't conclude that this thing converges by comparing it to 1 over 2 to the n. Yeah? So no use comparing. Because having a series that converges, which is less than your series, means nothing, right? You could have that a series that is bigger than a series that converges either converges or diverges. We have no idea. Yeah? You see what I mean? Yeah? Thumbs up if that makes sense. Cool. So, cannot do anything with the simple estimate. However, we have a tool that allows us to get around this, which is the limit comparison test. Because you can get the feeling that in its bones, this thing really is like 1 over 2 to the n, and it should be somehow that we can relate these two things. And in fact, that's true. So again, we need positive terms, and Bn are bigger than or equal to 0. And if the limit as n goes to infinity, an over bn equals L, which is bigger than 0, okay? Then, and the fact that the limit exists, I should also say, it's, in case there's any confusion, this thing has to be less than infinity, right? So this limit exists, it's some number which is bigger than 0 but less than infinity. Then, if the sum n equals 1 to infinity an converges, I better write that this way, then the series converges. Reciprocal implies that the other one converges. In other words, whatever an does, bn does, and vice versa, right? They are totally locked in together. Yeah? Which, to make this more vivid, I like saying that the series an and bn are married. Because once you're married, you either converge together or you diverge together. Okay? So this thing is like a test to see if you can marry the series an to the series bn. And if it's true, then Cupid fires its arrow and birds sing and the sun comes up, because they are married. And whatever they do, they have to do together. Yeah? Which means you can replace some ugly guy, some difficult guy, with some other guy, which is beautiful, whose behavior you understand. And we saw lots of examples of this. We can apply it to this right? So this is an ugly guy because we don't see what it's doing. It could be a lot uglier, but this is an ugly guy. Let's actually make it uglier. Suppose we have, let's call it Bn, not to repeat. Okay, yeah, let's call it An because we used it before. Suppose we have something even uglier like this, 2 to the n minus 3n squared, yeah, plus 5, say. This is an ugly guy, yeah? But if we look at this, we think, okay, 2 to the n is blowing up a lot faster than 3n squared because this is an exponential growth, this is an exponential function, this is the function x to the 2 to the x, right? So the dominant behavior on the bottom should be this 2 to the x. Yeah? So we think that this thing should be like this beautiful series Bn, just given by this. That's what we think, right? That's what intuition tells us, yeah? And indeed, if we try and see that this is true by taking the limit, so taking this limit as n goes to infinity of an over bn, then what do we see? That is the same as the limit as n goes to infinity of 2 to the n over 2 to the n minus 3n squared plus 5. And then we factor this 2 to the n from top and bottom. That's the limit as n goes to infinity of 1 over 1 minus over 2 to the n plus 5. And we see that this thing has to go to 1 because this term is going to 0 and this term is going to 0. Yeah? And you can either just appeal to the fact that you know that geometric series kill polynomials, or if you want, you use L'Hopital's rule to compare 3x squared to 2 to the x. Yeah? So this thing has got limit just equal to 1. Yeah? Therefore, these things are married. So you have married an ugly guy. You have married this ugly guy to this beautiful guy. Yeah? And you know that whatever this ugly guy does, the beautiful guy does, and the beautiful guy for sure converges. Yeah? Cool. So, you can rather easily reduce down questions of convergence for ugly guys to much simpler things by simply marrying them. And the art is just to look at one of these guys and ask yourself, what can I marry it to? So in this case, it was rather easy to guess because this was the dominant term. If we just change it a little bit, well, actually changing a lot. Suppose we have it like this. Again, the natural guess is that the thing on the bottom with the highest power is the leading order term. That's the thing that's really going to make the behavior that defines this thing. And sure enough, if we take this guy and try and marry it to this guy, it will still work. So as a rule of thumb, just extract off the leading order term on the top and the bottom, and then see what you get, and then try and marry it. Do this process. And if you do this, and you see that this limit exists, then you are reassured. You are absolutely certain that the actual behavior of your ugly guy is the behavior of your beautiful guy, and then everything is very simple. This is a very quick calculation light way to determine if series converges or not. Yeah? Cool. All right. So this was limit comparison test 11.5. So an alternating series is the following thing. So we have the sum from k equals 1 to infinity minus 1 to the k minus 1 bk, where these bk are positive. Okay? And there's nothing deep about this k minus 1. It's just a convention that we like the first term to be positive. So let's just write out the first few terms so you see what I mean. It's b1 minus b2 plus b3 minus b4 and so on, right? So we can't visualize this so easily as drawing blocks now because these are positive and negative terms. You know? However, a neat way to visualize this is to think about simply the action of somebody taking the sequence of steps. So your person starts here, does a step forward with b1, does a step backwards with b2, does a step forward with b3, step backwards with b4, and so on. Yeah? Cool. So we should think about this as what happens in the limit. This person going forwards, backwards, forwards, backwards, forwards, backwards, forwards, backwards. Maybe nothing's going to happen in the limit. Maybe this thing is this person's going to move forever. No? Or maybe something does happen. We have to think about it. So if we look at this picture, for sure, if the step sizes are not going down to 0, we already know by divergence test this thing can't possibly converge, and we see that our man is just going on forwards, backwards, forwards, and backwards, forwards, and backwards forever, right? So for sure, nothing. We can't say anything about that guy at infinity because he's moving forever. Yeah. Yeah. And what is interesting about this is that if these terms are decreasing, so this is alt series test or theorem. If bn plus 1 is less than bn, so that means these terms are decreasing, yeah? And the limit as n goes to infinity, bn equals 0, then series converges. And this is a major difference between an alternating series and a series of positive terms, because we're not asking the thing to go to 0 at any particular rate. Right? We're just asking it to go to 0. Whereas we know very well at this point that in order for a series to converge, if it's a positive terms, we need it to go to 0 fast enough, right? Because the series 1 over n doesn't converge, and if we go a little bit faster, it does converge. Yeah? Yeah? So this thing changes the game for us. And in fact, if we look at this picture, it's not really a surprise, because if these step sizes continually decrease, we see that the position of this guy or this person gets more and more restricted to a smaller and smaller interval, so that in the limit at infinity, the person going forward backwards is actually not moving at all, right? So think about you doing this, right? Take any sequence of decreasing numbers. You take a step forward by that first number, step back by the second, step forward by the third, step back by the fourth. Just practice this at home. Do this. Take a sequence of decreasing numbers and take your step sizes like this. You'll see that you get closer and closer and closer to some very, very narrow interval. And we can think about this and make this more precise. And that's the second key thing about this thing. If we stop at the nth step size, so suppose we keep doing this, and this is where we are. So we've just added bn. So this is where we are after doing n step sizes. Start again. After doing n steps, we are here, so at Sn, right? Where Sn, of course, is the sum from k equals 1 to capital N minus 1 to the k times bk. Suppose we are here, right? Then, let's change color to see what happens from this point on. We go backwards by bn plus 1, right? Then we go forwards by bn plus 2, which is less than bn plus 1. Then we go backwards by bn plus 3. And my writing is getting so small you can't see it. But what's the key point? The key point is after going backwards by bn plus 1, if we go by forwards by bn plus 2 and then backwards by bn plus 3, we don't get as far back as we were, right? And then we go forward by bn plus 4 and then back by bn plus 5. We are, again, not as far back as we were. Yeah? So we're never going to go past this line here, which we get from going backwards by the bn plus 1 step. Yeah? And for the same reason, we're never going to go forwards past this line here, right? Because the same reasoning, right? So we've gone backwards by bn plus 1. If we go forwards by bn plus 2 is less than bn plus 1, so it's not as far to the right. So we stop somewhere here. No? We go backwards by bn plus 3, but then forwards by bn plus 4. bn plus 4 is less than bn plus 3, so we're not as far to the right as this thing, which is less than this thing. Yeah? So forevermore, as we go forwards, backwards, we are between these two numbers, yeah? Given by Sn and then the step bn plus 1 backwards, right? Yeah? And the way I've set it up, I've done the bn step going forward. It actually could be going backwards, depends what n actually is. Yeah? But the point is the distance between where we are at the Sn step and where we are forevermore is less than the bn plus 1 step size. And we can just see it. You can just see it, right? So this picture gives us the following thing, that the remainder, I use capital N, is less than the bn plus 1 step size. Just this picture, right? Because this is Sn, and wherever we end up, suppose it's S, then the distance between these two numbers, S and Sn, is less than this bn plus 1 step size. Yeah? An easy picture. Well, easy. I say easy if you draw this and think about this. Like everything in math, it's either easy or incomprehensible. So if you draw this and think about this, and every single one of you can do this and be convinced of this, you will just see this and be convinced by it, and then it becomes an easy fact. You've seen me do this maybe 5 or 6 times. If you don't spend that, 10, 5, whatever minutes it takes to convince yourself that this is true, then it seems like a very complicated, weird thing. Yeah? But if you do spend that time, it's just going to click like this. And then it's an easy fact. Yeah? And that's how all of math understanding will happen. You will look at something, it seems incomprehensible, and then it'll fall into place, and then it becomes an easy fact, and then you're completely sure about it. All right, so this is true. And then this allows us to estimate how close we are to actual sums that we can't calculate, right? So this is the second test we have that allows us to do that. Allows us to get to with an arbitrary precision with a partial sum of something that we actually don't know. Yeah? Okay, so we're not going to do an example of this guy because we've already done it, but let's just do a quick example of testing a series for convergence. So, example, let's do this. Sum n equals 1 to infinity of -1 to the n plus 1 n squared over n to the 3 plus 1. Let's test this guy. Okay, so this guy is definitely alternating, right? It's going backwards, forwards, backwards, forwards, backwards, forwards. We need to check that this thing, so the bn, equals n squared over n to the 3 plus 1. We need to check that it's going to be such that if we recreate it, start again, we need to check that it's a decreasing, monotonically decreasing sequence that goes to 0. So need to check that bn plus 1 is less than bn, it's decreasing, and the limit as n goes to infinity, bn equals 0. So if you're doing a free response, you do need to show that you understand the theorem. So do not skip either part of this. It is clearly going down to 0, but it's no good if you just miss that. You will lose a lot of points. So do say this thing, even if you see it and think this is obvious. But this is indeed going down to 0 because the power on the top is n to the 3. It's going much faster than this thing, so this is going to 0. So we've checked it. Right? Now, this is the harder thing, right? So this is okay. We can either do some horrible algebra, playing with this expression, putting in what bn plus 1 is and bn, and I've done an example of this when we talked about it. And you could, if you fight hard enough with this, you'll actually be able to do it, but it'll be an awful, awful pain, right? Try this if you don't believe me. You can do it, but it'll take you a lot of at least a page and a half of careful estimates. The smarter way is to use the power of our tools from calculus, because we know how to recover this sequence with a function, right? So this is our bn. So the bn are positive terms, right? Because we use them to create our alternating series. So if we have a function that recovers this, then all we need to do is check that the function is decreasing. So find f such that f of n is equal to bn, which is n squared over n to the 3 plus 1. That's easy to do. Clearly, it's going to be this thing, x to the power 2 over x to the 3 plus 1. No? And then check it's decreasing, which means checking that the derivative is negative. Because if the derivative is negative, then for sure this is a decreasing function. So check that f prime of x is less than or equal to 0. And it needs to be decreasing from any number onwards, because we only care about convergence when we start from some finite point onwards, right? So check this is for all x bigger than some a, for any a. Okay, and then we just do the calculation, right? So f prime of x, it's going to be the quotient rule. Put everything under the bottom guy squared, x to the 3 plus 1 squared. Differentiate the top guy, 2x. Leave the bottom guy alone, x to the 3 plus 1. Minus, leave the top guy alone. Differentiate the bottom guy, 3x squared. And let's see what happens to this. Running out of space. So highest order power is x to the 4. So we have 2x to the 4 minus 4x to the 4. So we have minus x to the 4. And then we're going to have this just a 2x here. And then this is on over x to the 3 plus 1 squared. And then this thing is less than 0 for all x bigger than 2, right? So sure enough, this is a decreasing function, and we're all set. Yeah? So f decreasing, again, if it's free response, do write this. So f is decreasing. So this thing, call this star. Star is true. And that's it. That's all we need to do. Yeah? Cool. So we can quickly determine if something is converging or otherwise, if it's an alternating series, by simply checking that the limit goes to 0 and the terms Bn are decreasing. I think this is 11.6. I should really put ratio on root test because ratio is way more important. Okay, first, what is absolute convergence? So we say, now we're no longer necessarily dealing with series that have positive terms. Now that we got this method to determine if another class of series have positive or negative terms, we have the right to no longer always assume that a series has got positive terms. Huh? So we say a series, the sum k equals 1 to infinity, ak converges absolutely if and only if the sum k equals 1 to infinity, ak converges. So obviously if ak are positive terms, then it's exactly the same thing. Right? Okay, so example. The sum k equals 1 to infinity minus 1 to the k over k squared. Yeah? We know it converges anyway just by the alternating series test, but if we take the absolute value of these terms, it's just 1 over k squared, which still converges. Yeah? So converges absolutely. Okay? We say the series k equals 1 to infinity bk converges conditionally if and only if the sum k equals 1 to infinity of Pn converges but does not converge absolutely. So example, the sum from k equals 1 to infinity minus 1 for k over k. Yeah? Again, this thing clearly converges by alternating series test. These are decreasing sequence of terms going down to 0. But this definitely does not converge absolutely. When we take the absolute value of this, it's 1 over k. This is the harmonic series that diverges. Yeah? Cool. So we know that these are not the same concepts. Yeah? And in fact, there's a theorem. It's an easy theorem. I'm not going to prove it again. If the sum k equals 1 to infinity ak converges absolutely, then it converges. and this just follows easily from the comparison test. So let's represent the information of this theorem as a picture. Let's let this blob denote all the series that converge. Then inside that collection, there is a subset which converge absolutely. Yeah. But we know, we've already seen, that there are examples of things that still converge. So this is everything that converges. Okay, I'm not going to put that there. So this, let me put this in words. So the blob is everything that converges. Okay, but we've seen that there are guys that converge but do not converge absolutely, and those are the conditionally convergent guys. Okay, so the absolutely convergent guys are some strict subset of the set of all things that converge, and there are guys that still converge but do not converge absolutely, and we've seen an example. So this thing lives here, yeah? And this guy lives here. Okay, cool. And the fact that the absolutely convergent guys are inside the set of converging series is exactly the statement of this theorem. If it converges absolutely, then it converges in pitches. That's exactly that this blob is inside the larger blob. Yeah? Yeah? And it's a strict inclusion because there are things that converge but do not converge absolutely. And this theorem is useful for some series that otherwise we don't have any good methods for. So for example, this is the classic thing. Suppose we have cosine to the n over n squared. This is a sequence, these terms here are a sequence that are both positive and negative, right? Because cosine is doing this. So if you run through the integers, then cosine of n is definitely going positive and negative, right? But it's not alternating, right? Because whatever, this is pi over 3, which is like 1 point something, right? So as we go along this, then this will be positive, this would be negative, but the next guy would be negative, right? So it's not going positive, negative, positive, negative, positive, negative. Yeah? Yeah? So we can't just apply the alternating series test because that really needed it to go positive, negative, positive, negative, right? That's how we established this. Alternating series test was true in the error estimation test. So we cannot use alternating series test. This is not an alternating series. It's tempting to use it, but it's not. So don't fudge the issue if you do not claim that this is an alternating series test, because you know that it's not, right? This is a thing I sometimes see on exams, that students don't have a good idea, but they know something's going on, so they will like give it a go, give it a guess, right? So I've seen many, many exams where these kind of questions about this thing, and people say it's an alternating series. And I have a feeling most of them knew it's not an alternating series, but they just had nothing else in mind. Don't do that. Do not write things that you know is not true just in the hope of getting some partial credit. You will give your examiner the impression that you are just completely at sea, confused about basic things. So this is not like high school where your teacher's just looking for anything to give you points for. Here, when you write things that are incorrect, your examiner is thinking, oh goodness, they haven't learned basic things. And they are more unhappy with your exam. They are more critical when they continue to read through the rest of your solution. So do not write things that you know are not true, right? So this is definitely not alternating. Yeah? However, if we take the absolute value of this thing, then this thing is indeed less than this, because cosine is always between -1 and 1, right? And this thing converges, right? By comparison test. So by comparison test, the sum n equals 1 to infinity cosine of n over n squared converges. Yeah? And therefore, this series converges absolutely. That's exactly the statement, that this series converges absolutely. So converges absolutely. Which implies it converges. So therefore the series converges. So if you remember this principle, absolute convergence implies convergence, then you can handle guys like this rather easily. Yeah? Cool. All right. Everybody happy before I erase? We'll do one more board of content. Yeah? Okay. Ratio test. Okay, ratio test is one of the most basic useful convergence tests, and it goes like this. So if we have a series, and now we don't know if it's necessary you've got positive terms or not, so give some k equals 1 to infinity k. If, I don't know, I was going to say if it's a series, obviously it's a series, so a given series, where the limit as n goes to infinity of the absolute value of ak plus 1 over absolute value of ak exists, and it is less than 1, then series converges absolutely. Which therefore implies it converges. And if the limit as n goes to infinity of an plus 1 over an, this is some number, I think I want to call it L, just because that's what I did in class, is some number L, and it's bigger than 1, diverges. And if an plus 1 over an equals L equals 1, then we know nothing. Okay, so the way to think about this is as an X-ray machine to detect if a series in its bones has a structure analogous to a geometric series. So this is the key example. So if we have, say, ak equals r to the k, then ak plus 1 over ak equals r, right? Yeah, because each term is just r times the one before, right? So this is when you have the exact equality. This thing is saying that as we let k tend towards infinity, then this relationship is more and more true, right? So I made these positive terms. Actually, we don't have to. Let's make them like this. Yeah. Therefore, the absolute value of these terms satisfies the relation that each guy is just r times the last guy, right? So r could be a half, and then each guy is half of the last guy. Or r could be 0.9, and each guy is 0.9 of the last guy. Yeah? This approximate relationship, where we have a limit and an inequality, is just as good. This is just as good, because from this, then, so star implies that if we have large enough k, this is less than, say, L tilde, where L tilde is number which is just a little bit bigger than L, but it's still less than 1. Right? That's the definition of limit. Just draw the picture, you'll see this for yourself. And therefore, each guy is some fraction of the guy that came before it. Yeah? Which means that it is actually going down to 0 at a rate which is like a geometric series, or perhaps even faster than a geometric series. Yeah? So this is an X-ray machine to detect if your terms are going down to 0 at a rate like a geometric series or even faster. And if so, then for sure it's going to converge. Yeah? If, on the other hand, this limit is bigger than 1, that means each guy is actually bigger than the last guy. So these terms are actually blowing up to infinity. Of course, it's not going to converge. Yeah? And if we have limit 1, well, let's see. If we take, start a new part. So if we take ak to be 1 over k, then sure enough, ak plus 1 over ak is just going to be k over k plus 1, right? Which tends to 1, right? Or if bk is equal to 1 over k squared, then bk plus 1 over bk is equal to k squared over k plus 1 squared, which again tends to 1, right? And AK does not converge and BK does converge, but in both cases the limit is 1. In other words, we can't detect anything, so detects nothing. So our X-ray machine is only useful when we are detecting bone structure, right? Yeah? And if you have more subtle behavior that you can't see in the bones, then it isn't going to be seen with your X-ray machine, right? So if your series in its bones is like a geometric series, this X-ray machine will detect it. But if your series is not, and it's converging for other reasons, this thing tells you nothing. So it seems like a very powerful test, but actually it's less powerful than it seems, because this limit 1 happens really easily, really often, right? So don't think, okay, I'm just going to learn this guy because this guy does so many things. But no, it just does things in particular situations. So if you have a series that looks like it's a geometric series, that your feeling is it's a kind of a geometric series, then this thing will be the tool to use. So let's do a quick example. So this is an example. The sum k equals 1 to infinity minus 1 to the n to the 3 over 3n. Yeah? This thing, we're going to take the absolute value, so we're going to forget about this thing. The guy on the top is blowing up, n to the 3 is blowing up, but the guy on the bottom is also blowing up. And what your intuition should tell you is that this is something blowing up in a polynomial way. So we have x to the 3 is a polynomial growth, and the guy on the bottom is blowing up in an exponential way. X going to 3 to the x. This thing is absolutely slaughtering this thing. This thing is blowing up so much faster than this thing. No? So your intuition should say, okay, even though the guy on top is blowing up, I think that these guys overall are going down to 0 pretty fast, because it's the battle between this guy, and this guy absolutely kills it. Yeah? So you think, okay, so you take the absolute value of these terms, so consider the absolute value minus 1 to the n to the 3 over 3 to the n. And we have n to the 3 over 3 to the n. Yeah? And we think this is going down to 0 very fast. Seems to go. That's a very strange spelling. Seems to go. Very fast. In fact, fast basically like a geometric series. Because this 3 to the x is going so fast to infinity, this thing is barely even affecting it, it's barely slowing it down when we consider this ratio. So I should say that better. So this thing is going to infinity so fast that this ratio is barely slowing down how quickly the terms will go down to 0. It's basically going to go down to 0. We expect like 1 over 3 to the n. And then this ratio test is exactly the tool to test that. So we do ak plus 1, absolute value over ak, and what do we have? The ak plus 1 will be k plus 1 to the 3 over 3 to the k plus 1, right? And then divided by this thing, so we're going to have over 3 to the k to the 3. And then we have the 3's cancelled, so we have 1 over 3, and then it's just going to be k plus 1 to the 3 over k to the 3, right? And then this thing tends to 1, as you can see by expanding out. Should be easy. So overall, the expression tends to a third as k tends to infinity. So morally, each term is the third of the guy before it, yeah? Which means morally it's an awful lot like the series 1 over 3 to the n. Yeah? And sure enough, this means it's converging, so it converges. Absolutely. So it converges. Okay? So when you have something that looks like it's going to 0, like a geometric series, you can rather quickly test this with the ratio test. Yeah? Cool. All right, finally, the root test. Root test is extremely similar in concept, but it's different in form. So the root test is when we have the series, and we're going to look at this expression. We're going to take the nth root of the absolute value of an. Okay? And if this is less than 1, then it's good. If this limit as n goes to infinity, an is bigger than 1, then it's bad. And if the limit's equal to 1, then we don't know anything. Okay, and if the limit as n goes to infinity of the nth root of an is equal to 1, then nothing. Okay, so that is the root test. And what's it useful for? It is less useful than the ratio test unless you have something where taking the nth root simplifies the expression. So if an was something like 3n over 4n plus 5 to the power n, then let's make it exciting with a plus or minus 1. Yeah. Then if we do the nth root of the absolute value of an, then we get something rather simple. We just get 3 over 4n plus 5, which tends to 3 over 4, which converges. Yeah? So unless you have something where taking the nth root looks like it makes a rather simple expression, it's unlikely that the root test is better to use than the ratio test. And the way it works is exactly the same, right? Because the key example is if we have an equals r to the n, and then if we have the absolute value of an to the n is just r, right? So we know that this thing converges if and only if the absolute value of r is less than 1. Yeah. So what this thing is doing is trying to detect if in its bones the series is like a geometric series again, but it's doing it with a different in a different way slightly. Yeah? So sometimes algebraically it's more useful to look at this expression than absolute value of an plus 1 over an. Yeah? But basically, the philosophy behind the reason behind this test is exactly the same as the reason behind the ratio test. It's very good when you have things that you feel in its bones are like a geometric series or going to 0 fast in a geometric series. Otherwise, don't use this. Use something else. Okay, so we have gone from the start of the course up to the next section will be 11.7, which is just strategy. So it's pretty far. So after strategy, it's power series, where we learn about radius of convergence and interval of convergence, and then testing to see if not the endpoints work to find the interval of convergence, right? And then we learn about simple power series, given by the form after some algebra of 1 over 1 minus x, right? And then integrating, differentiating those guys. Yeah, and then we learn about Taylor series, which is the more recent topics. So in 3 classes, we cover 15 weeks, not 15 weeks. In 3 classes, we cover something like 12 weeks, right? And if you are on top of this, then probably you feel like fairly complete explanations have been given here, right? Because this is the effect. If you learn this stuff and you get comfortable with it, then it sort of compresses. It seems like there's less and less content. And if you don't understand it, it seems like a huge amount of content. So watch over these videos, continue to do a short summary for yourself, practice the things that you have difficulty with, okay? Focus on your weaknesses, go to the odd ordered exercises. At the end of 11.7, there's a whole bunch of series where they don't give you what test to use, and you just have to use these tests, practice that. That's an excellent thing to practice to see if you can do a series, you know? And if you do that, do some past midterms as well, cover the whole course. There'll be more of a weighting in later topics. You should be in good shape for the final and you'll do well. Yeah, this is just a function of how much you prepare. I now have office hours, so stick around if you have any other questions. Otherwise, I think this is the last class. So have a good exam and a great summer. And thank you to all of you who've continued to work consistently throughout this semester. It's been really helpful to me that you've been here. All right. Okay, before you go on, do you think the series converges or diverges? Okay, so yeah, the guy on top is dominated by this 9 to the n, and this is sort of insignificant, and the guy on the bottom is dominated by 8 to the n, so I agree. These terms look like they're actually blowing up to infinity, so I'd expect it to diverge. In fact, if we can just show that the limit of these things is not equal to 0, that's all we need to do. Yeah? So, looks like it diverges. And if the limit as n goes to infinity, 9 to the n plus n to the 4 over 8 to the n plus 5 to the n is not equal to 0, then for sure diverges. Yeah. Cool. So, we can check this out in a number of ways. So let's look at this thing. Since we think that this is going to go to infinity, the natural thing is to bound it below by something that is going to infinity as well. Yeah. Yeah. So as you say, the simplest first thing to do is to notice that this thing is definitely bigger than this, right? Because this n to the 4 just makes it bigger, right? So we do have this for sure. That's definitely true. And what makes it a little bit harder to understand is that we have this thing on the bottom, right? Yeah. And if we just had 8 to the n on the bottom, then it would be easy, because then it would just be 9 over 8 to the n, which is blowing up, yeah? But we can't just ignore this term because this thing does make it smaller, so we can't just drop it off, right? Because we want to bound this from below, right? Yeah. So we don't have the right to compare this to 9 to the n over 8 to the n. That's not true, right? However, 5 to the n is smaller than 8 to the n, yeah? So we could do this. We could do, because that's true, yeah? And what's that? That's just 1 over 2, 9 over 8 to the n. Yeah, and then, yeah. So you're applying more tools than you need to. Once you've seen that it was diverging, then the reason you think it's diverging is that these terms are going up to infinity, right? So the fastest way to conclude that is just to show that, and just doing some estimates with these expressions can get you there.